dear Professor and
hayot lazzatidan
participant.
bahramand.
I'm glad to participate in this climate resilient agriculture for ICA
Men
18 TSAE International Conference. I am going
rostlarda
to talk
mujassam.
about modeling and analysis of flow behavior in microscale hydroelectric turbine.
Yangi avlod
My
uchun
name is
yaratilgan
Jarbikov.
salam premium cola. Salom.
I am going to
O'zbekim.
talk about
Allergiya
introduction,
mavsumi yaqinlashib
work
kelmoqda.
map,
Zodik allergiyaning
electric
turli
consumption
alomatlarini
include
yengillashtirib 20
hours per
daqiqadan keyin
year.
ta'sir qilishni boshlashi
The
mumkin.
most
Zodik allergiya o'tadi,
country
hayot davom etadi.
Tabiat bu
using
ulug'vor.
to
U bizni
electric
har kuni yangi marralarni zabt etishga
China,
ruhlantiradi. Tog'li
India,
minerallar
and
muvozanati bilan
Australia.
boyidilgan Suv tabiiy
There
suvlar
are
siz
installed
ichingizda uyg'unlik
hydropower
manbasini
capacity
kashf
for the
etishingiz uchun
top
chotqol
10
tog' tizmasini
countries:
yuritgan
China,
ulug'vor
Canada,
Tian Shan o'rtasida
India,
tufayli
Nepal,
Suv
Laos,
uyg'unlikda buning.
Turkey,
Allergiya mavsumi
Indonesia,
yaqinlashib
Norway,
kelmoqda. Zodik
Vietnam, and
allergiyaning turli
Brazil.
alomatlarini yengillashtirib 20 daqiqadan
Next
keyin ta'sir qilishni
page
boshlashi mumkin.
of
Zodik allergiya o'tadi, hayot davom etadi. Lazzatli suvi bilan shahar
the
shovqinidan
turbines. There are classification of turbines.
mevali ta'm va tog'lar tarovati sen
Spelton,
o'ylaganda
Turco, cross flow, reaction, Kaplan, Francis, gravity, Archimedes, script, turbines, and other.
yaqinroq har yutum ila sen Tian Shan
There
tog'larini
are types of microscale hydroelectric turbines. 3D design for micro Kaplan turbine, micro Francis turbine, vortex turbine, Archimedes script turbine, Pelton while turbines. The, we used to micro Francis turbine because it's the most comfortable to uh, hydroelectric. Methodology: geometry of microscale hydroelectric turbine is built in console multiphase software. The turbine geometry includes a single inlet air runner with rotational leads and an outlet channel, typical of reaction tube microhydroturbines. The inlet has a circular cross section with a diameter of 1 meter, through which water enters in the turbine demand at three different volumetric flow rates: 1, 3, and 2. These values were selected to access in the influence of flow rate on internal flow behavior and performance metrics such as pressure distribution, turbulence intensity, and velocity profiles. In this study, the computational domain was decreased using unprecedented
allergiya
tetrahedral
mavsumi
elements,
yaqinlashib
which
kelmoqda.
offered
Zodik allergiyaning
flexibility
turli alomatlarini
in meshing
yengillashtirib 20
the
daqiqadan keyin
served
ta'sir qilishni boshlashi mumkin. Zodik
surface and
allergiya o'tadi,
internal
hayot davom
geometry
etadi.
of the turbine chamber. Near wall regions, particularly around the turbine blades and casing, were meshed with prismatic boundary layers to more accurately resolve sharp velocity gradients and turbulence effects. The mesh density was increased in zones of expected high flow activity to enhance numerical precision while maintaining a reasonable
Ba'zida
computational
muvozanatni tiklash
load.
uchun yagona istaging bu birgina ho'plam.
Result and discussion: the numerical results obtained from the finite
Maydami,
elements
kundalik
simulations
ritmimda.
provide insights
Salom
into
premium
the
cola.
internal flow dynamics and performance behavior of the micro hydroelectric turbine under warming flow rates: 3 volumetric flow condition 1, 3, 2, and outflow were simulated to evaluate the influence of inlet flow rate on velocity distribution, pressure drop, turbulence intensity, and potential efficiency indicators. Three different cut lines were applied to analyze the velocity and pressure distributions within the micro hydroelectric turbine. One cut line was positioned at the inlet section, the second at the bottom regions of the turbine near the blades, and the third at the outlet section. Result and discussion figure 7 presents the velocity magnitude distributions along cut line 1 in the inlet section. A micro-scale hydroelectric turbine for 4 different volumetric flow rates. The graph clearly demonstrates the increasing inlet increased flow rate results a corresponding rise in velocity magnitude throughout the domain.
Trend yaratuvchi.
At lower flow rates such as 1 meter cube second, the velocity field remains relatively stable with modest increases along the cut line as the flow rate increases to 2 and 3 meter cube second. A more noticeable acceleration is observed particularly when the midpoint of the cut line. Figure 8 illustrates the velocity magnitude distributions along cut line 2, which is illustrated in the bottom section of the microscale hydroelectric turbine for 4 different end flow rates 1, 2, 3, and over 4 meter cube seconds. The result indicates a distinct flow behavior compared to inlet section. At all flow rates, the velocity initial decrease. When this point, the velocity begins to recover and increases steadily along the cut line, indicating flow detachment or accelerating due to downstream geometric or pressure change. Conclusion: this study successfully deployed computational fluid dynamics to investigate the internal flow dynamics of a microscale hydroelectric turbine under varying inlet flow rates. The use of three-dimensional conformal phase model with a KE turbulence framework enabled detailed analysis of localized distributions, pressure fields, and turbulent structures within the turbine. The results clearly demonstrate that increasing inlet discharge leads to intensified turbulence, sharp pressure gradients, and more pronounced flow separation zones, particularly in critical regions of the turbine housing. These variations significantly influence the hydraulic performance and operational stability of the system. The insights gained from this analysis are instrumental for guiding future design optimizations aimed at enhancing flow uniformity, reducing resource relations effects, and minimizing energy losses. Overall, the numerical framework developed in this study provides a reliable approach for evaluating and improving the efficiency of micro hydro turbines under different hydraulic loading configurations. Reference, and thanks for your attention.